Welcome to The Explainer. What if everything you thought you knew about reality, space, time, gravity, was just completely upside down? What if the universe isn't this smooth, continuous flow we read about in textbooks, but something more like a giant digital computer crunching discrete chunks of data? Let's get right into it.
Okay, let's dive into this. I really want you to challenge your gut instinct about reality for a second. We all feel time as this smooth, never-ending river, right? But what if it's actually like a movie reel? You sit in a theater, you perceive smooth motion on the screen, but you're actually watching 24 individual, pixelated frames flashing every second. Could our entire universe have a literal frame rate?
You know, over 200 years ago, the brilliant mathematician Pierre-Simon Laplace had this absolutely incredible thought. He envisioned, and I quote, an intellect which at any certain moment would know all forces that set nature into motion, would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. That right there, that perfectly sets the stage for our overarching mystery today. We are looking for that single, unified theory of everything that bridges the tiny, weird quantum world with the massive cosmic scale.
Section 1. Is time actually pixelated? The limits of the continuous universe.
So for the last 100 years or so, physics has been kind of stuck. We've got this huge contradiction between Einstein's smooth, continuous universe on one hand and the rigid, choppy packets of energy in quantum mechanics on the other. But a massive breakthrough just came from researchers at the University of Augsburg and CUNY. They were studying something called quantum walks, and instead of a continuous flow, they found that quantum systems actually return to their initial states in discrete, quantized intervals. So at this microscopic level, time itself seems to step forward in rigid chunks, and the whole thing is dictated by these deeply mathematical topological structures called winding numbers. Crazy, right? Now, to actually prove this, they used a technique called ancilla coupling. Let's break down that heavy jargon because it's actually super clever. Normally, if you measure a quantum system directly, boom, you disturb it, you collapse its state. Ancilla coupling completely bypasses that by using an auxiliary or ancilla system to indirectly snoop on the primary system. This let the researchers watch these complex, multidimensional quantum movements without ruining the whole experiment. And by doing that, they proved that time's true nature at the quantum level is absolutely discrete.
Section 2. The quantum slit experiment. Visualizing discrete time steps.
Now, what's really interesting about this slide is how it shows exactly what a discrete tick of time does to reality. Take standard classical particles, the kind that follow definite, predictable paths. If you run them through a simulation using a discrete time parameter, something wild happens. Because time is clicking forward in steps instead of flowing smoothly, particles entering a force field near a slit actually get delayed by exact frames. This deviation creates these striking concentric circles. It forms an interference pattern that looks exactly like a quantum wave, even though there are literally no actual waves involved here.
And it gets even stranger. Because of this time discretization, the particle paths literally split apart, creating this Fresnel-like black region right behind the center of the slit. Absolutely no particles can land there. This bizarre, quantum-like void exists purely because of the mathematical frame rate of the universe. The particles just skip right over that physical space, completely bypassing it, all because of the discrete tick of the cosmic clock.
Section 3. Measuring the universal clock. Finding the physical frame rate of reality.
All right, we've looked at the visual models, but what are the actual numbers here? If the universe really is running on a discrete clock, how fast is it ticking? Shifting gears from abstract concepts to some hard, mind-blowing physical math proposed in the theory of universal origins, we hit this magic number, 1.3 times 10 to the negative 21st power seconds. That is the quantum of time. It literally represents the exact duration of a single tick of the universal clock. No physical event can happen, and no time can be measured in our earthbound labs faster than this tiny interval. It's the absolute limit of time's resolution.
And just like time is pixelated, space itself is quantized too. The research calculates that the absolute shortest measurable distance here on Earth is roughly 3.91 times 10 to the negative 13th power meters. Meaning space isn't just infinitely divisible, every physical distance you could ever measure is ultimately just a discrete multiple of this one fundamental quantum length. You literally cannot move half this distance. The universe just doesn't have the pixels for it.
Section 4. A new quantum gravity. Expanding the de Broglie wavelength.
Okay, we've spent a lot of time down in the microscopic world of subatomic ticks and tiny pixels of space. Let's do a massive zoom out. What does all of this mean for planets or entire galaxies? So, the crucial point is this. In quantum mechanics, the de Broglie wavelength tells us that all matter acts as a wave. Normally, we only apply that to incredibly tiny things like electrons. But this new theoretical framework says, hold on, this wave nature isn't just some quantum quirk, it applies to macroscopic objects too. Every massive object, a planet, a star, you name it, possesses an intrinsic, high-frequency wave that is directly equivalent to its mass. And what we experience in our everyday lives as gravity is literally just this macroscopic de Broglie wave interacting with space and time.
When you put these paradigms side by side, the contrast is huge. The standard model we got from Newton and Einstein relies on the inverse square law. Basically, gravity drops off really fast as you move away. But we know that math totally breaks down at the edges of galaxies, which is exactly why scientists had to invent invisible dark matter just to balance the equations. Now, look at the new quantum gravity model. It treats gravity as an exponential decay wave. Yes, it completely challenges classical geometry, but it acts exactly like Newton's laws up close and then bridges the gap perfectly across massive galactic distances.
Section 5. Solving the dark matter mystery. Unlocking the galactic edges.
Which brings us to the absolute climax of this explainer. If gravity is actually a quantized de Broglie wave, it has the power to completely eliminate one of the most frustrating mysteries in modern astrophysics. When you take this new wave-based exponential gravity formula and stretch the math out to its absolute extreme limits, what we call the extragalactic regime, something incredible happens. Gravity doesn't just keep fading away into nothing. Instead, the math dictates that it flatlines. It becomes a constant. And when you know it, this perfectly matches the observed flat rotation curves of galaxies. Those outer stars are spinning incredibly fast, not because they're swimming in a halo of invisible dark matter, but because the fundamental wave nature of gravity dictates that the force simply stops decaying at those massive distances.
And this brilliantly illustrates the raw power of this new framework. Take the Magellanic Cloud's halo mass. The standard general relativity model completely underpredicts it at 2.2. The dark matter model has to artificially inject a bunch of invisible mass to push it to 4.0, which matches what we actually observe. But check out the quantum gravity model. By simply applying that quantized wave formula, it naturally predicts a mass of 4.08. That is stunningly accurate to the actual observation, and it does it without needing a single particle of ad hoc dark matter. Dark matter is literally rendered mathematically obsolete.
So that leaves us here with one massive question. If time ticks in exact, discrete increments of 1.3 times 10 to the negative 21 seconds, if space is literally pixelated at its foundational level, and if gravity is just the macrowave expression of those quantum rules, is the universe we live in less like a smooth, continuous physical space and more like a high-resolution, frame-by-frame rendering? The evidence we've looked at today for sure points toward a reality that is far stranger and way more structured than we ever imagined. Thanks for hanging out with me for this explainer, and remember to keep questioning the nature of your reality.